But we are here today to see the talk by Ayse Coskun, that is a full professor at Boston University at the Electrical and Computer Engineering Department, where she leads the Performance and Energy-Aware Computing Lab to solve problems toward making computer systems more intelligent and energy efficient. Coskun is also the director of the Center for Information System Engineering at Boston University. Coskun's research interests intersect design automation, computer system, and architecture. She received the IEEE Council EDA Ernest Q. Early Career Award in 2017 and currently serves as the Deputy Editor-in-Chief of the IEEE Transactions on Computer-Aided Design. Coskun received her PhD degree in computer engineering from the University of California at San Diego. So, Ayse, thank you very much for accepting our invitation. It's a great pleasure to have you today to talk about a very interesting subject. So the floor is with you. And now you should put your slides in presentation mode as it is now. So the floor is with you.
Thank you so much, Ricardo. It's a pleasure to give a talk to the CASS community. So today I'm going to talk about modeling and optimizing chip cooling through machine learning. As Ricardo mentioned, I'm a professor at Boston University. If you have questions, feel free to ask during the talk, at the end of the talk, or via email later. So temperature of chips has been an active area of research. And many different types of work have been done over the years. So what I'm going to talk about today is the issue of long simulation and optimization times when you want to optimize your chip along with an on-chip cooling technology. So what I'm going to argue and show you solutions for is we need to enable fast and accurate thermal analysis on chips. And as part of that, we need to have a tool that can provide rapid and accurate selection of the optimal cooling solution for your given chip. So let's review why removing heat from chips is important. So like I mentioned, that this has been an active area of research already. Power density has been increasing over the years. And it's saturated at some point, but the power density overall is very high. So it causes high temperatures. Many chips today operate near their thermal design power budget. A related issue with temperature is leakage power. So higher the temperature, the higher the leakage power. So this is essentially wasted power. This is the power consumption that chips consume even when they are not actively processing. So it's so important to keep an eye on the leakage. It's important towards energy efficiency purposes. And as some of you might know, temperature also is related to reliability of devices. Higher the temperature, lower the reliability. So that's why we have to keep our chips operate at safe temperatures. As an example, DARPA started, and this program has finished, but DARPA started the Ayse Cool program for designing new on-chip cooling systems about a decade ago. It was very successful. Many new solutions came out of it, including for liquid cooling. So there's a lot of interest in this topic from academia as well as in industry. We want to compute more. We want to do more complex computations, which comes at the cost of higher power and higher power density, which results in higher temperatures. So we have to handle high temperatures to enable safe, efficient operation. In tandem, there has been a number of emerging cooling methods that are being developed. Liquid cooling is one of them. Thermoelectric coolers, devices essentially that are put on the chip to remove localized heat, is another method. Having liquid cooling through microchannels and optimizing liquid cooling along with thermoelectric cooling is a hybrid cooling method that my group has demonstrated. And there are other methods such as evaporator structural devices that are put on chip to remove heat in an efficient way. So one important message here is that there are a number of methods coming out from thermomechanical engineers, essentially. So an important message here is that there is no obvious winner for which chip, which cooling, and using which cooling optimization parameters would be a better fit. Some of these techniques would be better at removing localized heat. Some of them would be potentially more expensive in terms of their power consumption if they are active method and their overall cost. Some of them would be better for mobile. Some of them would be better for servers. And because there is no obvious winner, one needs to design the cooling method along with the chip, and we can call this co-design of computing and cooling, and optimize the cooling for a given chip to improve efficiency substantially. So we need a comprehensive cooling optimization framework that can work with a given chip architecture. And then we can look into the power maps or power distributions over time, steady state and power transient power curves for a given chip. And then given this chip and power profile, we need to design a cooling system. So we need to go through a cooling optimization flow so that we can select near optimal cooling solutions and their near optimal parameters for a given chip and power profile. So this is the way to improve efficiency beyond the current limits, of our systems. So a method that's been commonly used for rapid thermal evaluation is compact thermal modeling. So traditional thermal models prior to compact thermal modeling, they were using finite element methods or computational fluid dynamics-based simulation. So for instance, COMSOL or ANSYS are commercial tools that are available today. You can model your system in them and get accurate, assuming you can parameterize the model accurately, you can get accurate results through these type of tools. However, they take a lot of time. They take a lot of memory. So doing many simulations to evaluate a new architectural improvement, looking into transient responses that you might want to do to evaluate runtime behavior, these are not feasible using finite element methods. So compact models have been the de facto standard for fast and accurate modeling methodology in architecture, in EDA, and they rely on the duality between electrical and thermal properties. So what happens is that we model basically temperature in terms of heat flow, a temperature drop, and thermal resistance. So we go from a representation of the chip into an RC network that represents the heat flow. So each node generating power becomes a current source. Resistors model the thermal resistivity, basically thermal heat flow across different components on the chip, and the capacitance models the thermal time constant, essentially. So the entire chip then can be modeled as a lump RC network. And the good news here is that we know how to solve RC resistor capacitor networks. So essentially, we use differential equations, as you see in the equation, and we solve these differential equations to compute the temperature, if this is a thermal model. So, however, this does not solve all the challenges. So, for instance, if you are generating a new cooling method, and I've been working with collaborators, particularly at MIT, Evelyn Wang and her group, and they design new methods, and they often have computational fluid dynamics type of simulations for their new devices that are for on-chip cooling. So there's a mismatch basically in what the architecture and EDA communities expect in terms of the ability to simulate with compact models versus the new devices models. New devices models are in CFD simulation. So these can take, like I mentioned, long simulation times up to days for even running a simple simulation and large memory requirements, which make these infeasible. For instance, if you want to do an architectural improvement and see the impact on temperature, you typically want to do thousands of simulations, if not more. So we need to get rid of this costly CFD simulation. And then when you are looking into these new cooling devices, They are parameterized. So basically, depending on the thickness of the cooling device, depending on the temperature of the cooling device, depending on the flow rate of the liquid, for instance, in liquid cooling, all of these parameters affect how much cooling you can accomplish on the chip. So exhaustively searching all possible parameters of a given cooling mechanism is too costly. So we need a better optimization algorithm, which we address, and then I'm going to talk about in this work. So our candidate to help solve these challenges is machine learning. So machine learning models can be fast and lightweight. And for instance, you can train a machine learning model to predict the computational fluid dynamic simulation results. So as opposed to running a CFD simulation for every single experimental setup that you want to evaluate, you can have a model that predicts the result for you. And this achieves substantially faster results. And deep learning models can also help predict the cooling optimization results. And we can consider power maps of chips that are similar in a way to unstructured data that deep learning methods are very good at today. So the key takeaway that I hope people will get out of this talk is that combining a compact thermal modeling method with machine learning models enables rapidly and accurately predicting the optimal cooling solution, as well as its cooling parameters for arbitrary given chip designs. So I'm going to talk about how to enable fast and accurate compact thermal simulation. I mentioned that compact thermal models are the de facto way to do architecture or EDA-based thermal simulation. However, there are some challenges with that, and I'm going to discuss Pact as a way to address those problems. I'll talk about machine learning and how it can enable modeling emerging cooling methods in a rapid way and in an accurate way. And then I'll talk about how to optimize these cooling methods using deep learning. So let's talk about Pact first. So I'm going to talk about the simulation flow and how to extend it, to provide some results. I'll also touch upon a case study that we've done for an industry partner. So like I mentioned, there are, this area is pretty mature. There are many different papers that you'll find if you are looking for thermal modeling, even for compact thermal modeling over the last decade or two. However, there are some weaknesses of existing compact thermal simulators. So if you take any of the compact models that are out there, they would work fine. They would be accurate given if your assumptions in the model are accurate. However, often these models fail when tackling complex problems. For instance, if you want to model in detail a 3D stack and you want high granularity in your simulation, or you want to emulate a really large chip that might be necessary for like a 2.5D stack system, or you want to do fine granularity simulation to match your thermal model with the granularity of a standard cell level circuit simulator. And on top of that, there are some models out there for modeling a specific cooling technique. Like there's a model for liquid cooling, but there's no tool that is readily supporting emerging cooling methods in an extensible, easy to extend way. So there are other methods in addition to compact models, like green functions. They rely on basically simulating an impulse, temperature impulse. However, they are very fast. However, they require a lot of pre-characterization, which is a problem. As you change the chip, you need to pre-characterize the model again. And SPICE-based thermal modeling, when we started this work, we found it to be very promising because SPICE essentially is a circuit simulator. It is a good simulator for simulating RC networks. And essentially, if we are using circuit components for modeling thermal behavior, then SPICE might be a good fit. So this is where Pact came out. And Pact is our parallel and compact thermal simulator. It's available on GitHub. It's already being used by other research groups. And it has a SPICE backend. So the front end is a Python front end that you can interface with. And the inputs are on purpose designed in a similar way to Hotspot so that researchers and the community who have been using Hotspot can basically start using Pact in a rapid way. The key difference of Pact, or one of the key differences, is the backend. That's a SPICE backend that's using SPICE, so it's highly parallelized and it can achieve really immense speedups, especially in transient simulation space. We observed up to 200 times improvement when you are doing thermal simulation in terms of the running time of your simulation. And the accuracy matches that of equivalent compact thermal models such as hotspot, and the error is within a few percent of computational fluid dynamics-based simulators such as COMSOL. These are all expected. And it's highly extensible. It's designed in a modular way, and it already comes with some cooling libraries that we provide, but it's easy for a user, we believe, to come in and provide their own cooling method if necessary. And it actually can work with standard cell level or architecture level. So depending on the granularity needs of the user, that can be adjusted. So this is Pact thermal simulation flow. The user provides the chip stack, normal 2D chip, 3D chip, some others, 2.5D chip, etc. And the number of grids, basically the granularity and what kind of heatsink, what kind of cooling method. And then our tool automatically generates the netlist components given the cooling libraries. And then this the user can also select the solver, because the backend is now SPICE. There are many options in SPICE simulators on how to solve differential equations. And you can trade off, for instance, accuracy versus speed in some of these solvers. And some of these solvers may or may not converge given the size of your problem, but it's possible to tune that. So then you have an output that gives you the thermal results for each grid cell on your chip. You can represent it as in terms of the grid cell. You can lump them into micro architectural components and the like. So I mentioned that the tool is easily extensible. So for instance, I'm showing here the liquid cooling method. So it comes as a library that can be, that basically enables modeling of liquid cooling. And then it's parameterizable, so you can change the properties of your liquid cooling based on your microchannel dimensions and the number of channels, your fluid density, your fluid parameters like the coolant velocity and the like. You can parameterize this model easily and then generate a thermal net list accordingly and send the result to the SPICE engine. So SPICE engine, because this is SPICE circuit simulator, it's already parallelized. It can run really fast on clusters. So most researchers would choose to use a cluster of some sort to run many simulations when they are doing temperature, energy, or architectural research. So if you have access to multiple machines, you can really see substantial speed up already. So we also demonstrated how Pact can be integrated with OpenRoad. So OpenRoad is it's a project for open sourcing EDA tools, and it has stages for synthesis, placement and routing, logic gate parsing, OpenSDA, and so on. And basically, we interface the power map generation with Pact, and then get the standard cell level power map and feed that into Pact. And Pact's granularity is completely tunable. It can work from standard cell all the way to architecture level or coarser grained if necessary. But at the standard cell, it's possible to integrate this, and still you can run it. Basically, typically, there is a cost or running time and accuracy trade-off. So you can get finer granularity, but then at some point you just get prohibitive simulation times. In the case of Pact, because it's fast and parallelizable, and you can select your solver, this is actually a practically feasible solution. Basically, for steady state and transient, I mentioned there are a set of simulators available in SPICE simulators for differential equation solvers. So you can select depending on your need. Like I mentioned, you can select something that's faster, you can select something that's more accurate. All of this is possible, and we evaluate several of these solvers in our paper. We also provide visual Pact, which generates either pictures or videos of your thermal maps. We find this to be a useful tool, not just to make pretty pictures for presentations, which is also nice, but also to visually inspect what's going on in a system. And I'll show you a case study in a little bit for this visual Pact, like how it can help you actually see this. So one important thing to note is that A thermal simulator alone is usable, but needs to be integrated with something to get the power value. So I mentioned OpenRoad integration if you want to do standard cell level simulation. Another option is to combine Pact with architecture level tools. We demonstrated integration with Sniper. We demonstrated integration with also MacPath as the power modeling tool. So you basically get the architecture level performance results from Sniper, then MacPath generates the power numbers, which you should calibrate typically for your given specific chip. And then you use Pact to generate the temperature for the architectural components, and you can feed this into Visual Pact. Similarly, instead of Sniper here, you can use something else like Gen 5, other architecture level tools, or like I mentioned, you can use OpenRoad if you have chips that you are modeling at the standard cell level. So when we did validation with OpenRoad benchmarks, we saw highly promising results. So like I mentioned before, the comparisons to finite element methods that are modeled for the equivalent chips and cooling mechanisms, we see a difference of less than 3% error. And this is similar to what any other compact thermal model typically would experience, such as hotspot. So we got good error rate, and our results, as you see on the right side here, matches that of hotspot in terms of the runtime transient response as well. And our difference from, again, ComSolve in terms of the transient is also around 3%. So when we look at speed, so maybe it's worth mentioning this in detail. Hotspot is a commonly used tool, and it does perfectly fine unless you get into these, like I want to do really detailed simulation, or I want to simulate a larger chip, or I want to do a 3D stack, and I want to model each layer of the 3D stack, or you want to model a cooling technology in more detail. So unless you get into these more complex scenarios, Hotspot is used. I've used it many times. I developed some models initially as part of Hotspot, so it's fine. And as you see on the graph here, the steady state simulation time for small problem sizes would be similar between Hotspot and Pact. Where Pact becomes important, the speed of a Pact, is when your problem size is larger, which means you either are emulating a larger chip, or you want to do more detailed simulation, like I mentioned, like because you have an interesting cooling technology or 3D stacking and so on, or you are getting into the transient space where you want to run transient simulations over longer time instances, and then Pact can make a tremendous difference, like up to almost 200 times. So generally speaking, smaller problem sizes or coarser granularity, Pact and Hotspot are pretty equivalent. As the problem size gets bigger, or the grid size gets bigger, or like finer granularity, then Pact starts to show substantial improvement. So we were fortunate that a company approached us. This company was generating synthetic diamond heat spreaders, and they wanted to evaluate their technology. So we used Pact to evaluate their technology as a real-world case study, and we published our work at Interpack. So if you are curious about diamond heat spreaders, you can take a look. But it was an opportunity for us to evaluate our tool and compare also the usual computational fluid dynamics type simulators. And Pact did a really nice job here to be able to evaluate different kinds of options, different chip power densities, different thicknesses of the heat spreader, and so on. So basically, the simulation time not being a bottleneck enables you to do a lot more simulation than you could have done otherwise, right? So, so we were fortunate to do that. I'm not going to get into the detail due to lack of time, but it's worth taking a look here. So this was a case that we presented to the company, and then along with our presentation. So on the left, there's a typical copper spreader. On the right, there's a diamond heat spreader. You can see already what are the hot spots on the chip. And on the right, the diamond heat spreader is doing a much better job, and it reduces the hotspots by over 20 degrees. So this is also coming from Visual Pact. I mentioned that in addition to making nice pictures for your presentations, which is a nice feature, like I'm using it right here, this type of visual output gives the user or the designer the opportunity to explore problems. Like the hotspot might be in a location that you did not expect. The hotspot might be going on for a longer time than you anticipated. So all these things are I believe, visually sometimes very obvious, and it's harder to sometimes see it in text files. So a visual Pact combined with Pact enables this. So let's talk about machine learning. So far, I haven't gotten into machine learning at all. I talked about Pact, which is using a SPICE backend. It's enabling much faster execution of compact thermal models. Now let's discuss a little bit more about modeling emerging cooling methods and how machine learning can play a role. So existing cooling methods over the last decade or two, people, including myself, we developed models for emerging cooling methods, such as liquid cooling via microchannels, hybrid cooling of liquid cooling. And typically what you do is for a regular circuit, for the compact model consists of a current source, a resistive element, and a capacitive element, like I mentioned. When an emerging cooling method comes into play, you immediately think about what circuit elements can I put in. So for instance, do I put a dynamically modifiable current source, or do I put some sort of a different element? Do I split into multiple cells where I can model a thermoelectric cooler cell versus a liquid cooling cell differently? So all this is done, and then Pact also involves liquid cooling models, by the way. Hotspot has some work that they have in their recent work. They integrated liquid cooling. A team, by the way, that Janze from EPFL have done a liquid cooling model. So there are some compact models out there. However, what we wanted to model, based on the latest advances from our collaborators' lab, was to model a two-phase vapor chamber. So what's a two-phase vapor chamber? It's a passive cooling element, which is very attractive, because one issue with liquid cooling-based solutions is that typically liquid cooling needs to connect to a pump that's going to push the water into the chip, and then it's going to collect the water back and then cool it and then feed it back to the chip again. And that consumes power. Whereas a two-phase vapor chamber is a passive element, so the operation mechanism is that the coolant absorbs the heat from the chips and then evaporizes, so you have vapor, and then the condenser condenses the coolant back into a liquid state and feeds it back into the evaporator. So this is the mechanism of it, and you can see a picture over here. The major pro is the high heat transfer rate, and then there's no power needed on the evaporator side. But the cooling performance relies on the design of this evaporator. So it could be single wick, hybrid wick. Micropillar is single wick typically, and then hybrid wick, which we were interested in, use a nanoporous membrane and some microchannels. So the evaluation metrics of this is heat transfer coefficient, basically how much heat is transferred, and the dry out heat flux, which is related to the evaporation. So like I mentioned, there are different ways to implement this. An issue with single wick or micropillar-based evaporators is that the transfer coefficient and the dry out heat flux are conflicting with each other. So it's challenging to optimize both these parameters to improve cooling efficiency. That's why thermomechanical engineers designed hybrid wicks. Basically, there's a nanoporous membrane that provides a high transfer coefficient, which is desirable, and then microchannels enhance the dry out process, dry out heat flux. So this increases permeability. So, okay, I mean, this is one cooling technique, and you can do different types of emergent cooling methods using our method. So the important step is here to convert this into a compact thermal model. In this case, our initial model assumes constant temperature above the evaporator, and then we abstract the vapor chamber layers, and we have to model this vertical thermal resistance of the vapor chamber. So you see on the right, there's the liquid part that is modeled as a different cell, and the vapor is modeled as a different virtual node in the simulator. And then to be able to compute this thermal resistance, once we have the thermal resistance, we can fall back onto our RC network, right? But to compute this thermal resistance, we need HTC, high heat transfer coefficient. And this is a temperature-dependent function and typically needs an iterative simulation framework. So how typically people approach this is to generate HTC correlations, basically using a computational fluid dynamics model like COMSOL. So you basically study what your heat transfer coefficient will look like using a detailed CFD model. However, this works in terms of the accuracy. However, it still takes hours and potentially days, depending on how many entries you want to generate for your HTC lookup table. So if you want to do something really exhaustively, like generate 1 million different entries for HTC, it's going to take you a couple of years running just on one machine CTM. So, okay, let's say you are okay with just a few thousand entries. It would still take you a day to generate an HTC table. And a day doesn't sound too scary if you were to do this once. However, what we typically want to do is to tweak a lot of things and do a bunch of simulations, right? So as researchers in EDA, architecture, circuits, we want to do a lot of simulations to optimize the system. So we said that we have to do something with this. So instead of exhaustively searching to generate a complete HTC table, why not use machine learning here? So machine learning basically looks into the parameters of this cooling method to generate the heat, to generate a model that's going to be able to predict the HTC given your coolant properties, your dimensions, and so on and so forth. So we generated a random forest-based model, and for each different coolant type, because you can change the coolant as well, you can generate a different model as well. And you basically do a model using a small, relatively much smaller number of experimental cases, and then you have a machine learning model that can predict, given a particular parameter or given set of parameters for the coolant, what the HTC will be. And then you can use that HTC in your thermal model and model your overall cooling system. So when we validated this with not using machine learning and doing actually exhaustively generating all the HTC numbers, we received accuracy reaching almost 99%. And we tested it out with different floor plans, so we got very promising results. So again, the overall idea is to, as opposed to generating a heat transfer coefficient table using a CFD simulator for thousands of entries and doing a very comprehensive job about it, let's do it maybe hundreds of entries or like thousands of geometries, but then it's able to predict for millions of different types of geometries. As you change your chip, as you change your geometry, you can predict the cooling heat transfer coefficient in this way. So we then improved this model for two-phase vapor chambers. So like I mentioned initially, we had the assumption of using constant temperature above the evaporator. Then in the improved version, we added vapor core modeling, condenser modeling, and transient simulation. So now the updated version essentially generates new cells for the condenser as well as the vapor core, provides more detailed modeling, and it does not have to assume this fixed temperature on the evaporator. So how does this work? Improved temperature-dependent HTC simulation framework. Basically, it's iterative simulation. So you can start, let's start from the top right. You have the hybrid wick geometry, you have the temperature distribution, you have some coolant properties. You generate either HTC correlation lookup tables exhaustively using your CFD simulator or using our machine learning method. You generate a model for predicting the heat transfer coefficients. And then you do an iteration to see if the error is within the range that you are looking at. And then you can parse these HTCs, calculate the thermal simulation, to calculate the thermal resistivity to input into the thermal simulation engine, and then compute the temperature. So you can iterate in this way, and therefore you can compute the temperature impact on the heat transfer coefficient. So once you have these models, you can actually compare different cooling methods for your chip. You can change the parameters of each coolant. And then, for instance, compared to just a copper heat spreader, the two-phase vapor chamber can provide a lot of improvements, over 10% reduction in the hotspot, which is a big number if you think about it, like if you are going from 90 degrees to 80 degrees, for instance. You can optimize your system using these models to fine-tune basically the copper thickness, vapor chamber thickness, and so on and so forth. We showed results that basically this passive cooling method is very promising for high performance chips. And one problem this kind of approach addresses is that it enables us, like I mentioned earlier, to co-design the cooling and computing system together. Basically, it gives you the ability to tweak parameters both in your chip and your cooling system and optimize them together to improve efficiency substantially compared to the state of the art. So one other application of using machine learning is to get detailed thermal maps. So knowing where our hotspots are can allow for more energy efficiency, right? If I know where my local hotspot is, for instance, I can think about putting a thermoelectric cooler on it, or I can do some architectural modification to reduce the hotspot, or maybe I have a system level policy to reduce pounding of that on that particular hotspot with more workload. So all of these are possible if I know the location of a hotspot. And typically this is done through thermal sensors on chips. The problem is that we can't put thermal sensors everywhere. Real estate is very competitive on a chip, as you may know. So I can't put thermal sensors everywhere. And different workloads and core mappings actually change the location of hotspots. So the location of hotspot could also be dynamically changing. And on top of that, sensors are not perfectly accurate. So typically they come within a degree of accuracy margin. So what we did, instead of relying on the few available sensors on the chip, can we actually come up with a method to learn the thermal map behavior of a chip and predict temperature across different points of the chip, which would essentially tell me where the hotspots are. So the model inputs are thermal sensor measurements, total chip power, workload core mappings, and then we train a model that's going to learn the relationship between the input power map and the temperature and the hotspot locations and all. And in this way, it can actually tell us the temperature map as opposed to exhaustively simulating for every power map. And we got very nice results. So compared to the golden known heat map, it's predicted the heat map is actually having very high R2 scores and very low root mean square error. And so this is a promising method when you want to predict temperature of a chip based on few thermal sensor measurements. And we did cross-validations, basically training with known applications and known core count, and then training with these type of known information. And then what if there's an application that I haven't seen before that's running on the system? And we did this type of validation, and overall, we still got very good results. Of course, you know, as you increase the number of unknowns, like if I'm only training a system when my only 2 cores are active, but I keep bringing test cases that are 4 cores, 8 cores, 10 cores active on my chip, then there might be a mismatch. But assuming you have relatively representative test set for all your possible cases, then through that representative set, you can learn the thermal model of the chip and predict using machine learning. So what are some limitations of these compact models or these approaches that I discussed before I get into a new section? And the compact thermal models today, even with Pact, can fail, and you want to make the grid size very small. Grid size is basically the individual unit where you are computing temperature. So if you are getting below 300 nanometers square, for instance, you need to consider quantum effects and Boltzmann transport to be able to model temperature effectively. The good news is that most researchers out there don't need to really consider this kind of really tiny grid sizes. In fact, like when you look into the literature, you'll see a lot of people doing temperature simulation at the architecture level. I mentioned standard cell level is possible today. We have integrated, as I mentioned, Pact with OpenRoad. So you can go directly from your chip model to a full thermal evaluation, and that's great. And you can do it really fast, so you can actually look into transient effects as well. However, eventually, for instance, for future emerging devices, when we want to model the fine granularity effect, like the tiny grid sizes, we will need to include Boltzmann transport equations and quantum effects, and then basically change some of the modeling we are doing. So that's one future direction. We always can use more validation with real test vehicles for both for the chips as well as for the vapor chambers. So especially for emerging cooling technologies, validating with real world test vehicles is often a challenge. It may or may not be available. We were able to do this work because of our collaborators at MIT, Evelyn Wang's group, who were designing these methods, but not everybody has access to these. So more test vehicles, more results out of these test vehicles would be essential for the community to get their hands on new cooling technologies. So limitations of the heat map prediction I mentioned using machine learning. So far, we've done only steady state. It's possible to do it at transient level, but we haven't demonstrated it. So if you are looking for your next paper in temperature, this could be a nice next paper, basically doing transient prediction using machine learning. Of course, it would be great if we put in some work to do a IR camera validation of this method as well. But overall, I think this is a promising direction, and one could work on proving the generality of the machine learning model as well. So, and what's next? Can we actually optimize cooling methods for high-performance processors using machine learning or deep learning? So I mentioned one cooling method. So if you are not into vapor chambers or micropillar wick apparatus, that's okay. But I think the approach, we strongly believe actually, the approach is applicable to a variety of different cooling methods. So bear with me, even if you are, this is not your dream cooling method, because, you can basically replace some of the parameters here with some parameters from another cooling method and still apply the machine learning framework. So the goal is to, given a cooling technology, select the best possible dimensions, in this case, best possible micropillar wick geometries that maximizes the heat transfer coefficient while meeting the dry out requirements. So HTC is basically, you want the HTC heat transfer to be high, right? And then there's a dry out requirements. Basically, this is coming with the, because of the Twophase, the liquid will evaporize, there's going to be dry out, so you need to meet certain constraints over there. And then we want to pick the option, the geometry that has the highest HTC. So then you can do a grid search, right? So you can say that these are my parameters. You can see a table here, nanoporous membrane thickness, pore diameter, porosity, aspect ratio, this and that. And all of these have some valid range, which you can learn from your thermal mechanical engineer friends or from the literature. And, these are the ranges. So I can do a grid search. I can just search exhaustively. However, it's going to obviously take a lot of time. So instead, we started with Multistart simulated annealing. Maybe if you are not familiar, simulated annealing is an optimization approach. We do Multistart because simulated annealing guarantees finding a local optima given a problem, but it may be stuck at a local optima. So we do Multistart and start the same problem, optimization problem, multiple times to increase the chances to find the global optimum. So we tested with different hotspots, different background heats, different coolants for micropillar wick. And overall, we were able to show that using this type of an optimization approach, you can find better geometries that's going to improve your HTC, while you can get speed up of several times for finding the optimal solution compared to the grid search. So Multistart annealing, is supposed to taking, for instance, 20 hours. You can do this with Multistart simulated annealing in 2 hours, so which is a substantial improvement. So this is you can think about this problem as a black box optimization method. So how to select the best cooling method, and it could be several different methods. So you can have vapor chamber as one candidate, liquid cooling, thermoelectric cooling. Just putting a heat sink could be an option, right? So you can put all these cooling methods along with their tunable cooling parameters. And then the black box optimization essentially will find the best cooling method with its optimal cooling parameters. For instance, it can tell you that, I'm going for this system, the best option is to put a bunch of thermoelectric coolers on the chip. Or for this option, it will be liquid cooling with these parameters of the liquid flow and so on and so forth. So for this, initially, we used the covariance matrix adaptation evaluation strategy, which is the CMA-ES you see in the middle over there. So you do the vapor chamber optimization, for instance, power profile, floor plan, etc. You run simulations, and then you output your system, and then you generate a chip stack, and then you do, for all cooling candidates, this type of CMA-ES optimization, and it generates you the optimal cooling solution as well as its parameters. So it's a nice optimization method. So you start with your chip and your target cooling mechanisms, and then you find which one is the optimal along with its parameters. There are some issues with this. Essentially, when it's, I mentioned over here that we were using simulated annealing, for instance, to figure out the coolant parameters, right? Or the cooling technology parameters. Here, there's a similar problem. So you have several cooling technologies and a bunch of parameters for all of them. And even if you use an efficient optimizer like CMA-ES, you're essentially doing a lot of search to find the optimal cooling parameters. So black box optimization is fine, but it doesn't scale well as you have more cooling methods and more parameters. So even for a 64 by 64 type of grid, which is pretty conservative, you typically want to do hundreds by hundreds type of grid cell, at least if not more. It takes 2 hours. Again, 2 hours is not scary, but this is just one simulation for finding the optimal. You typically will do a lot of these. So we moved from there to using machine learning for also finding this optimal cooling parameters. So instead of doing a grid search or an iterative search across many different parameters, can we actually use CNNs, convolutional neural networks, to select the best cooling method along with its cooling parameters to solve a goal function, basically minimizing cooling power while meeting your temperature constraints. So we pre-process the data, standardize the power maps, and then we have a hybrid cooling CNN architecture that is going to traverse across different types of methods and how to combine them. And for instance, for Twophase, it's going to create a CNN architecture to compute nanoporous membrane thickness, microchannel porosity, microchannel aspect ratios, and so on and so forth. And at the end, generate the optimal cooling solution along with its parameters. So the data preparation stage is basically dividing the chip into some uniform grids. We use, to generate synthetic power maps, we use gamma distribution. You can use a different distribution, or if you have a lot of real-world power maps, you can use that instead. And then we augment the data, and we determine the objective function of what we want to optimize, so essentially. So we standardize the power maps, and then we determine the objective function. And we design a multi-output CNN regression model. It's multi-output because, like I mentioned, each cooling method often will have multiple different parameters that you can tune. And it's very hard to know, even for an expert, to know in advance what are the best parameters, what are, and if I set my microchannel porosity to a particular value, what should the diameter be? So it's very hard to know these. So the benefit of this multi-output CNN model is that it's going to compute all of these automatically by training on a much smaller model. So the results were very strong. So we trained with tens of thousands of data points, which is not that big, considering that you might be evaluating millions of different options. And as a result, overall, R-square values were very high in the well into 99% range. And mean square errors and the like were very small, less than 2% in most cases. So we looked into optimization for realistic chips, overall evaluating the error. Average error stays within a few percent. And the error is basically with regards to predicting the optimal cooling. So a few percent is very manageable, considering that we get substantial speed ups. We got basically 2 orders of magnitude speed up in finding the optimal compared to doing a grid search. So these are different chips coming from the Pico 8595 and the like. These are chips coming from the OpenRoad benchmark sets. And then overall, we got a maximum temperature difference of less than a degree, cooling difference of 0.01 watts, and like I said, 2 orders of magnitude difference in speed up in finding the optimal cooling solution. So if you're interested in this, some open problems improve changing the objective function to include more information about manufacturing cost if that information is available to make it more comprehensive. We believe that there's work to do on the CNN architectures to make it finer granularity, maybe include more parameters about chip size and chip thickness to truly make it a co-design tool, as opposed to basically optimizing solely the cooling parameters. You can also optimize the chip parameters with using a framework like this. It would be possible to expand this to support emerging integration methods, 3D, monolithic 3D especially, and then create a systematic way to train neural networks for emerging integration. And runtime, basically, you can also look into optimizing the runtime. For instance, with liquid cooling or thermoelectric cooling, there are parameters of the cooling methods that actively you can change at runtime. And potentially, it's possible to use neural networks to optimize the runtime operation as well. So in summary, I talked about a way to enable fast and accurate parallel thermal simulation with Pact. And there's a GitHub repository. Please check it out. And this achieves a substantial improvement in terms of the simulation speed compared to known compact thermal models, especially if you have emerging technologies like 3D, 2.5D, if you have new cooling methods, or if you have large problem sizes. I encourage you to try Pact. And I showed that modeling emerging cooling methods by training machine learning models gives accurate and fast results compared to training or building these models using computational fluid dynamics type simulators. And finally, I showed briefly how to optimize cooling parameters using deep learning and how to design convolutional neural networks to predict the optimal cooling methods, cooling parameters for among several given cooling methods. So these are the publications. You can check it out. It's on our website, and feel free to let me know of any questions. I'd like to acknowledge my PhD alum, Zihao Yuan, who graduated recently, and he was the primary author in much of this work. And I acknowledged already Evelyn Wang, and I also acknowledged Sherif Rida, and we collaborated extensively in much of this work together. Thank you, and happy to take questions if there are any.
So thank you very much, Ayse, for your very nice talk. So I have a question here by Shintauf Mohammed. So I assume that the vectors are needed to generate the heat map. Is it okay to provide RTL stimulus, or it should be a gate level, FSDB or VCD?
Thank you for the question. So I believe the RTL stimulus, so basically this is related to what kind of power input to generate the heat map when we are doing standard cell simulation, as far as I understand. So it depends on your needs. So if RTL stimulus is sufficient for the accuracy of the power, and then that should be sufficient. Basically, we use whatever power information is coming out from the standard cell tool. In this case, OpenRoad has a particular way of generating the power maps, so we use that information. So if you have a different method for generating the power input, and that's accurate enough for your purposes, it should work. I don't see any problem. Hopefully that answers the question.
Okay, thank you. Chantal has a second question. By the way, Chantal is attending the talk now from Morocco, and he is with Mohammed V University.
Thank you.
So the second one is also, what is the requirement in terms of coverage? Does the tool do any propagation for activity estimation or of messy nodes?
This is probably related to generating the power maps, I'm guessing. So if you have activity estimation, like whatever you are using for activity estimation, you can use that. So what we did, for instance, when we are generating for the convolutional neural networks, we wanted to generate a whole bunch of power maps so that, we have thermal maps and then we can train a model. We use the gamma distribution so that we assign basically positive power values within a range to all different nodes. So you can use a method like that to generate a large amount of power maps that's going to provide. We don't have a specific number for like this percentage is needed for coverage. But overall, you want a representative set, and that depends on the specific system. So I can't really, I'm not able to provide a number, but I would think about like, this is the chip, what's the possible space, and you can have a high level estimate of like, do you have tens of thousands of millions of different power maps, and in that range, what's a good number? Like, do you want to just generate maybe 1% of possible settings or 1.1% of possible settings? Hopefully it makes sense. But that's what I would recommend, basically having a rule of thumb or a general guideline of how much coverage you might have, and using some sort of a random distribution to generate the power maps. In addition, one could do, sometimes designers have a lot of power maps handy already. This is not the common case, but sometimes it happens. And you are particularly interested for a small number of, like really learning a small number of power maps that represent the real world behavior. In that case, you can use a much smaller set of power maps.
Okay, thank you very much. I see for the moment, no more questions in the YouTube channel. So if someone still have a question, please do it very quickly. But I have one.
Sure.
So all these cooling systems using water or other liquids, how big is the cooling system?
That's a great question. So for liquid cooling, traditional way to do this would be to have microchannel cooling on the chip or on the package. Sometimes you don't have to do microchannel. And then you connect this to a pump that's like physically sizable. So typically there would be a pump per rack of a data center, for instance. And then the pump would push the liquid, and then you would collect the liquid back into the pump. So that's the typical liquid cooling scheme. With vapor chambers, we are talking about devices that could be put even on embedded systems. We are talking about micrometer scale chambers that are just done using advanced material science and thermomechanical engineering techniques to get the, and you put some liquid in there, but liquid is always there. Essentially, it's basically sucking the heat and vaporizing the liquid, and then collecting it back within a small device. So it can be, I believe, some companies even showed prototypes on cell phones of this type of small-scale liquid cooling technology. So it depends, is the answer. But like I said, traditionally, people were designing like bigger pumps and liquid cooling with active power to push the liquid. But these vapor chambers can be passive, and they could be put on embedded systems as well.
Okay.
So it is, there's a cost associated, which we didn't get a chance to explore too much with the fabrication cost and everything. Hopefully another researcher can look into that.
So all these cooling systems, they are very feasible for a large system, data center, and so on. But for portable systems, there is an extra challenge.
Yes, that's true. But like I was saying, the vapor chambers are essentially passive devices. They don't require external power.
Oh.
And they are small scale, so they could be put on some smaller systems and embedded systems even, potentially. Actually, we show that for some of the systems, actually, when you go to really high power, typically liquid cooling becomes a really viable option. But if for medium power density systems, like in the case with some embedded systems, vapor chambers becomes really attractive. So I think it's a mix, basically. It's not just data centers. And what cooling method is the best for you changes depending on your chip.
Okay, thank you very much. There is another question still by Chantal. So, was there any post-silicon post-fabrication validation done, or is it only against the sign-off thermal tools?
Great question. So we have not validated the model with silicon post-fabrication. However, so there are several answers to this, I guess. The validation of compact models have been done many times, including by our group in the past. So comparing a compact thermal model with actual measurements. So that was done, even though not recently. Validation of modeling of emerging cooling devices, that also has been done by our collaborators, but for the cooling device alone. So a validation including the chip and the cooling system for the model versus the actual measurement for the full-scale system hasn't been done. So it's challenging, but it's really interesting. And if you are interested, I would be happy to chat more.
Okay, so thank you very much.